Hello everybody, get ready to do lesson 6.5 part 2 of pre-calculus math today. And today as classwork, you got 8 points here, students, on your that go into your notebook or your notebook guide. And then you got 42 points here that will go into your classwork sheet. Hopefully you have your classwork sheet and your homework guides ready, your notebook guides ready to go. And no bell work today. We go right into a notebook. Multiplication and division of complex numbers. The trigonometric form adapts nicely to multiplication and division of complex numbers. Suppose you are given two complex numbers. Z1 would equal r to the 1 cosine theta 1 plus I sine theta 1, and Z2 would be r2 cosine theta 2 plus I sine theta 2. The product of Z1 and Z2 is, here we are. Here's your product here. R1, R2 cosine theta 1 plus I sine theta 1 times quantity cosine theta 2 plus I sine theta 2. So there'll be your product right here of product of Z1 and Z2. And then we can put this into bracket now. We're going to use properties here, trig properties here. So we're going to group here like terms together, and then we have our sum and difference rules of trig functions. This case here, this is a sum and difference rule for cosine and sine. So this is what we end up with. R1, R2 is bracket cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus I times quantity sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 bracket. So there we have our product here for the product of Z1 and Z2. Okay, moving into our second page here for your notebooks. Here we have our product here, and because of this R1, R2, we have cosine theta 1 plus theta 2 plus I sine theta 1 theta 2. This is due to the sum and difference formula that we have used before. So now let's go into product and quotient of two complex numbers. So for let Z equal R1 cosine theta 1 plus I sine theta 1 and Z2 equals R2 cosine theta 2 plus I sine theta 2 be complex numbers. So Z1, Z2 now will equal R1, R2. Here's our product here, cosine quantity theta 1 plus theta 2 plus I sine quantity theta 1 plus theta 2. Here's our product here. And now here will be our quotient. Z1 over Z2 would equal R1 over R2 would be bracket cosine quantity theta 1 minus theta 2 plus I sine quantity theta 1 minus theta 2 bracket. And in this case, R2 cannot equal 0. And then this is our quotient, what our quotient will look like here. So this is what you model your problems off in our homework for product and quotient of two complex numbers. Let's try an example now of these properties. Multiplying complex numbers in trigonometric form. Find the product of Z1, Z2 of the complex number Z1. It would be 3 times quantity cosine pi over 4 plus I sine pi over 4. And Z2 would be 2 times quantity cosine 3 pi over 4 plus I sine 3 pi over 4. Okay, Z1, Z2. So now we multiply this by this, and that's symbolized, or it's enumerated, or it's alliterated. It's alliterated down here. So we end up with 2 times 3 is 6, and then cosine pi over 4 plus 3 pi over 4, we combine like terms, plus I sine pi over 4 plus 3 pi over 4. Again, we combine like terms. And once we do that, we end up with 6 times cosine theta plus I sine. This is 6 times cosine pi plus I sine pi. And what's the cosine of of pi would be negative 1 plus I times the sine of pi would be 0. So we have 6 times negative 1 would be negative 6. And then this would be your quantity here. This is Z2, and then this is Z1. So when we add these two vectors together, we get negative 6 for that, which is out here. So Z1, Z2, Z1 times Z2 would be negative 6 on our real axis here. This is a real number here, negative 6, and that's illustrated down here. Let's go into an example now. Perform the operation and leave the result in trigonometric form. So we have 2 times cosine pi over 2 plus I sine pi over 2 bracket, and then 5 times cosine 3 pi over 2 plus I sine 3 pi over 2. So 2 times 5 is 10 times quantity cosine pi over 2 plus 3 pi over 2 plus I sine of pi over 2 plus 3 pi over 2. So here is our product here, moving from this stage down into this. And then when we continue with the product process here, we have 10 times cosine 2 pi plus I sine 2 pi. Then 10 times cosine of 2 pi would be 0, plus I sine out here, the sine of 2 pi would be 0 as well. Okay, so multiplying complex numbers in trigonometric form. Again, find the product of Z1, Z2 of the complex numbers. Z1 equals 2 times quantity cosine 2 pi over 3 plus I sine 2 pi over 3. And then Z2 would equal 8 times cosine 11 pi over 6 plus I sine 11 pi over 6. So here are our two different members of our product. So we need to multiply these two together. Here is our line up here of a product. So we have 16 times cosine 2 pi over 3, and then we bring this over here, 11 pi over 6 plus I sine 2 pi over 3 plus 11 pi over 6. Then we end up with 16 cosine 5 pi over 2. So when we add these two together, we get 5 pi over 2 plus I sine 5 pi over 2 here. These add up to 5 pi over 2. And that would become 16 times cosine pi over 2 when we factor out a full cycle, which would be 2 pi out of this. We get 2 and 1/2 pi. So we just end up with pi over 2, cosine pi over 2 plus I sine pi over 2. And then that becomes 16 times 0. This is 0 plus I times 1. And that is 16i would be the product of these two quantities there. So, knowing that, you can check this result by first converting to the standard forms. So Z1, when we convert this over, we get negative 1 plus radical 3i, and Z2 is 4 times radical 3 minus 4i. And then multiplying algebraically, we get Z1, Z2. When we multiply these two together, we get these two binomials here. And then when we FOIL them out, we get negative 4 times radical 3 plus 4i plus 12i plus 4 times radical 3. We combine like terms and it comes out to 16i. So when we check it algebraically, it checks with our trigonometric form. Let's try one now. Perform the operation and leave the result in trigonometric form. So here is a trigonometric form here between these two quantities. Independent practice, I'm not sure if I do this, I might do that. But anyway, up here for 67, we start out here by multiplying these out here, 2/3 times 9, and then cosine 4 pi over 3 plus 5 pi over 3. We combine our like terms here, and then same thing over here, 4 pi over 3, and then 5 pi over 3. And then that gives us 6 times cosine, this is 6, cosine 3 pi plus I sine 3 pi. And when we factor out a 3 here, we get rather, well, not that, we just we factor out one period here, which is 2 pi, and we end up with 6 times cosine pi plus I sine pi for our product here. Then down here, I'm going to let you do that. Do I do this? Nope, I'm going to let you do it, students. Let's move on to the next example here. Example 7, dividing complex numbers in trigonometric form. Find the quotient. Find the quotient here of z1 over z2 of the complex numbers. And so z1 is 24 multiplied by quantity cosine 300 degrees plus I sine 300 degrees. And then z2 will be 8 times cosine 75 degrees and I sine 75 degrees. So here is our quotient here. And we're going to divide 24/8. We're going to group like terms here. Cosine 300 minus 75 degrees. So 300 minus 75 degrees. And then sine 300 minus 75 degrees. And then get 24 over 8. Multiply times bracket cosine 300 minus 75 plus I sine 300 minus 75. Just to pound that in so you don't miss it. I think you got that. So the next step here would be 3 over cosine 225 plus I sine 225. And we get 3 times, when we put this into exact values here, we get negative a radical 2 over 2 plus I times a quantity negative radical 2 over 2. And then when we multiply that out, we get this quantity here, the negative of 3 times radical 2 over 2 minus 3 times radical 2 over 2i is what our solution is for that quotient. Let's try a quotient down here, okay? So perform the operation and leave the result in trigonometric form. So here's our quotient for 73, cosine 50 degrees plus I sine 50 degrees over cosine 20 degrees plus I sine 20 degrees. So first, we're going to combine like terms here. Cosine 50 minus 20 plus I sine 50 minus 20. When we get that, we get cosine 30 degrees plus I sine 30 degrees. It says leave result in trigonometric form, so here's your trigonometric form for that. And then do I do this one down here? I'm going to let you, if you're in my classroom, I'm going to let you do this. If you're at home school, do this before you check your answer. And yeah, I would test yourself on this one, and I don't do it. So haha, you have to get the solution PowerPoint. Okay, powers of complex numbers. The trigonometric form of a complex number is used to raise a complex number to a power. To accomplish this, consider repeated use of the multiplication rule. So here we have z would equal r times quantity cosine theta plus I sine theta. And then z2 here, it would equal r times cosine theta plus I sine theta r. Cosine theta plus I sine theta equals R2 here. In this case, R2 would equal cosine 2 theta plus I sine 2 theta. So powers of complex numbers, this is the way that you would show powers here, is by multiplying out your powers. And then a z3 here would be R2 times this, and you end up with R cubed here would be cosine 3 theta plus I sine 3 theta. Okay, I think we have that. And then z to the fourth would be r to the fourth cosine 4 theta plus I sine 4 theta. And then z to the fifth would be r to the fifth would be cosine 5 theta plus I sine 5 theta. This pattern leads to de Moivre's theorem, which is named after the French mathematician Abraham de Moivre, 1667-1754. De Moivre's theorem, here it is. If z equals r cosine theta plus I sine theta is a complex number and n is a positive integer, then z to the nth would equal r cosine theta plus I sine theta to the nth power, which again will mean that it equals r to the nth equals cosine n theta plus I sine n theta. So this page 9, this goes in your notebook. Students, teachers, let your students enter this in their notebook. Give them time to do that. These are very important aspects here. Okay, let's go on to our next example. Example 8, finding the power of a complex number. Use de Beauvoir's theorem here to find 1 plus the radical 3i to the 12th power. So first convert the complex number to a trigonometric form using r equals radical 1 squared plus radical 3 squared equals 2, and theta equals arctan radical 3 over 1, which is the same thing as pi over 3. So the trigonometric form is, knowing those parts of the statement, we have 1 plus radical 3i equals 2 times quantity cosine pi over 3 plus I sine pi over 3. Then by de Beauvoir's theorem, you have 1 plus the radical 3i to the 12th power. So now when we know our power here is 12, we have 2 times cosine pi over 3 plus I sine pi over 3 to the 12th power. Once we have that, we have 2 to the 12th equals cosine 12 pi over 3 plus I sine 12 pi over 3. Can we simplify that further? I think we can. 4096 equals 4096 multiplied times quantity cosine 4 pi plus I sine 4 pi, which equals 4096 equals, this is 1 and then this is 0, so it ends up to being 4096 for that product using that power property. So let's try one. Use de Beauvoir's theorem here to find the indicated power of the complex number. We have 1 plus I cubed here, and down here for the independent we have 2 plus 2i to the 6th power there. To find the indicated power of the complex number, write the result in standard form. So for up here, we're going to use square root of 2 multiplied by cosine pi over 4 plus I sine pi over 4 cubed here. This is all cubed because we have this cube here. 1 plus I. If you graph this 1 and 1, you get a 45-degree angle, and this is what gives us our cosine pi over 4 and sine pi over 4. Oh, wait a minute, that one's out of order there. I'm going to jump down here, students, for you to help you down here on your independent practice here. 2 times radical 2 multiply. Again, we have a 45-degree angle here. Cosine pi over 4 plus I sine pi over 4 to the 6th power. And then we're just going to take everything to the 6th power here. So this becomes cosine 6 pi over 4, sine 6 pi over 4. And then this is to the 6th power here because of this 6 here. And then that hashes out to 512 times, so when we simplify this, it'll be cosine 3 pi over 2 plus I sine 3 pi over 2. So that's your independent. Up here, well, let me finish. Negative 512i. Let's see here. How do we get that? Negative 512i here. See, cosine of 3 pi over 2 would be 0 here plus 1. So we have a negative 1 actually. This would be negative 1. So we have negative 512i for this power problem here. Up here, you didn't do. You have to do that on your own. So that is 6.5 part 2. Here's my email if you need classwork sheets, homework sheets, solution PowerPoints, or anything else for this course. This is my email. Thank you very much.